Welcome back to the channel. I'm excited to dive into one of the most fascinating topics in machine learning today, autoencoders. Whether you're a beginner trying to understand neural networks or an experienced developer looking to implement dimensionality reduction, this video is for you. Before we begin, if you're finding value in these deep learning tutorials, smash that like button and subscribe for more AI content. Let's unlock the power of autoencoders together. So, what exactly is an autoencoder? Think of it as a neural network that learns to copy its input to its output. But here's the twist. It's forced to learn an efficient, compressed representation of the data in the middle. Imagine you're trying to compress a high-resolution image. An autoencoder does something similar. It takes your input data, compresses it into a smaller representation, and then tries to reconstruct the original data from that compressed version. Mathematically, we can represent this as f of g of x approximately equals x, where g is our encoder function and f is our decoder function. Every autoencoder has three main components, and understanding these is crucial for mastering autoencoders. First, we have the encoder. This part takes your input data and maps it to a low-dimensional latent space. Think of it as the compression algorithm that extracts the most important features. Next is the latent space, or bottleneck. This is where the magic happens. It's the compressed representation that captures the essence of your data in fewer dimensions. Finally, the decoder reconstructs the original input from the latent representation. It's essentially trying to reverse the encoding process. The beauty is in this bottleneck. By forcing information through this narrow passage, the network learns to identify and preserve only the most important features. Now, how do autoencoders actually learn? The training process is beautifully simple yet powerful. Autoencoders use reconstruction loss, typically mean squared error or binary cross-entropy. The network tries to minimize the difference between the input and the reconstructed output. The loss function looks like this. L equals the norm of x minus f of g of x squared, where x is our input and f of g of x is our reconstruction. During training, gradients flow backward through both the decoder and encoder, adjusting weights to improve reconstruction quality. It's unsupervised learning at its finest, no labels needed. As training progresses, you'll see the reconstruction loss decrease, meaning your autoencoder is getting better at capturing the essential patterns in your data. One of the most powerful aspects of autoencoders is their ability to learn efficient representations. But what does this really mean? Let's say you have 1,000 dimensional data. An autoencoder might compress this into just 50 dimensions while retaining most of the important information. That's a 95% reduction in size. The encoder learns to identify patterns, correlations, and structures in your data. It automatically discovers which features matter most for reconstruction. For complex data like images, autoencoders can learn manifold representations, capturing the underlying structure of your data in a smooth, continuous space. This enables smooth interpolation between data points in the latent space, creating new, meaningful variations of your original data. Autoencoders come in several flavors, each designed for specific tasks. Let's explore the most important types. Vanilla autoencoders. The basic autoencoder we've discussed, straightforward encoder-decoder architecture, focused on dimensionality reduction and feature learning. Denoising autoencoders. These are trained on corrupted input but asked to reconstruct clean output. They learn robust representations that ignore noise, perfect for image denoising and data cleaning. Variational autoencoders, VAEs. VAEs add a probabilistic twist. Instead of deterministic encoding, they learn probability distributions. This enables them to generate entirely new data samples. Sparse autoencoders. These enforce sparsity in the hidden layer, meaning only a few neurons are active at once. This leads to more interpretable feature learning. convolutional autoencoders. Perfect for image data, they use convolutional layers to preserve spatial relationships while learning hierarchical features. Let's implement a simple autoencoder using Python and TensorFlow. I'll walk you through every step. Here we're building the encoder. Notice how we progressively reduce dimensions from input to latent space. After training on MNIST data for 50 epochs, you can see how well our autoencoder reconstructs handwritten digits. First, autoencoders are unsupervised. No need for labeled data. They automatically discover patterns and features in your dataset. Second, they're excellent for dimensionality reduction, often outperforming traditional methods like PCA for complex, nonlinear data. Third, they're versatile, useful for compression, denoising, anomaly detection, and data generation. Finally, they learn meaningful representations that can be used for downstream tasks. However, autoencoders aren't perfect. They can be prone to overfitting, especially with limited data. The quality of reconstruction heavily depends on your architecture choices and hyperparameters. For very high-dimensional data, training can be computationally expensive and time-consuming. Also, vanilla autoencoders aren't great for generating new data. That's where VAEs and GANs excel. Image processing. Autoencoders excel in image denoising, super resolution, and compression. Companies like Netflix use them for video compression algorithms. Anomaly detection. In cybersecurity and fraud detection, autoencoders learn normal patterns. Anything that doesn't reconstruct well is flagged as anomalous. Recommendation systems. Netflix and Spotify use autoencoders for collaborative filtering, learning user preferences from sparse rating data. Drug discovery. In pharmaceuticals, autoencoders help discover new drug compounds by learning molecular representations. Data compression. From image compression to sensor data reduction in IoT devices, autoencoders provide intelligent compression that preserves important information. Let's wrap up what we've learned today. Autoencoders are powerful neural networks that learn efficient data representations through self-supervised learning. Key takeaways. They compress data into meaningful latent representations, learn without labels, and have diverse applications from denoising to anomaly detection. Ready to dive deeper? I recommend starting with the implementation we showed today. Try it on different datasets, images, text, or time series data. If this video helped you understand autoencoders, please give it a thumbs up and subscribe for more deep learning content. Drop a comment below about what type of autoencoder you'd like to implement first. Thanks for watching, and I'll see you in the next video. Keep learning, keep building.